Okay, I think we're good to get started here. The quiz that you guys took on Friday on limits wraps up that topic of limits. We're done with that for now. The next place we're going in a textbook is chapter 9, specifically 9.1 through 9.4 is sequences and series. Target date for our first quiz for this stuff is going to be a week from today, just to give you an idea of the next assessment. Say something else. For the quizzes on Friday, the scores are posted in Genesis, but I haven't released them yet in Edulastic because I still have a couple makeup issues that I'm dealing with. As soon as they're taken care of, they'll get released. All right, that's the where we are, where we're going update. Anybody have any issues or concerns before we get started? All right, as far as the terms, sequences, and series, sequence just refers to a number pattern, like 2, 4, 6, 8, 10. Very often when you're dealing with number patterns, it's necessary for the small part of the bigger problem to add them up. Once you start adding the terms of a sequence, then it becomes a series. But as far as we're concerned, for just everyday language, sequences and series, we could just consider to be patterns, basically, is what we're going to be doing here. All right, as far as the overall structure of the first 4 sections of this chapter, which is kind of going to be our own like mini unit here, 9.1 introduces basic vocabulary and basic notation for sequences and series. 9.2 is going to focus on one specific type of sequence, an arithmetic sequence. 9.3 will focus on just geometric sequences. 9.4 will focus just on quadratic sequences. So today our goal is we're going to do the intro, which is relatively quick. It's not like this is your first time seeing number patterns. And then we'll do 9.2, which is the arithmetic patterns. Tomorrow is a half day, so we have shorter classes. So basically, tomorrow is just finish up what we don't get done today. I don't see any reason why we can't get through the notes. For the most part, tomorrow's class should be just finishing up last night's homework, get a chance to ask some questions. Good with that? All right. On to the notes then. Okay, an important overall note for all of what we're doing in 9.1 through 9.4. When you're working with number patterns from a formula, the most common beginning point is to have your n or your k, whatever the variable is for the problem, to begin at 1 or 0. Okay, you're assuming 1 unless you're told otherwise. So the first term is your a sub 1. There are patterns where your first term is an a sub 0, and there'll be something specific within the problem to indicate that. So for our first 2 examples here, it says write the first 5 terms of the sequence defined by the explicit formula, and it's giving us a formula. It doesn't say anything in there about n starting with 0, so it means n starts with 1. Now, looking ahead a couple problems to this one here, we have an a sub 0. So an a sub 0 means you start with that as being a sub 0 being the first term. All right, I didn't leave very much room here. I apologize when I made up this note sheet, so I'm going to spread it out a little bit further here so we can see some more details. So our formula that's defining this sequence is a sub n is equal to 2n minus 3. N stands for the number of the term. Unless you're told otherwise, you assume you start with 1. So you're going to plug a 1 in, plug a 2 in, plug a 3 in, plug a 4 in, plug a 5 in, do your order of operations, and that defines our first sequence here. So 2 minus 3, 4 minus 3, 6 minus 3, 8 minus 3, 10 minus 3. So those are the first 5 numbers of our sequence. Now, just reinforcing that original vocabulary, if we were to then add them up, put plus signs in between them, then the sequence becomes a series. All right, something that's a little bit higher up the food chain in terms of the formula that we have to plug into here. So no matter how complex or what this looks like, we're plugging the numbers 1 through 5 in to get first 5 terms. And then it's just order of operations. Now what happens here, if you have -1 raised to successive whole number powers, it's just going to cause this to flip-flop back and forth between positive ones and negative ones. -1 to any even power is going to be a positive 1. -1 to any odd power is going to be a -1. So in terms of just kind of going ahead with that, that's just going to be -1. That's basically just 1. It drops out. That's going to be a -1. That's 1. It just drops out. That's going to be a -1. And then we can kind of concentrate on the rest. So times 1 plus 5. So that's going to be a 4. So that's going to be 4 plus 5, 9. That's going to be a -1 times a 9 plus a 5. -9 plus 5 is -4. That's just 16 plus 5. And then this is going to be 25 plus 5. So -25 plus 5. Brain for you. -15? No. Lie. -20? Now, one thing that's going to tend to happen when this idea of a -1 raised to a successive powers becomes a small part of bigger problems later in the chapter, the basic effect it has, it causes our terms to alternate signs. Like this is kind of an outlier, but from this point forward, all the rest of them are going to be positive, negative, positive, negative, positive, negative. So this is kind of a little preview of something that's going to come a little bit later that's going to be pretty important. All right, everybody okay with those? All right, now, a part of the instructions that I kind of glossed over without paying specific attention to was that explicit formula. If you have an explicit formula, you can find any term you want without knowing any of the other terms around it. So for example, if we wanted the 150th term of this pattern, we just have to plug in 150. We don't need to know terms 100 through, numbers 1 through 149. Now, in contrast, another type of formula, going to the next section, write the first 5 terms of the sequence defined by the recursive formula. Okay, another term for a recursive formula is an implicit formula. Depending on what website you go to, what book you read, they're about equally used. So what happens here is in a recursive or an implicit formula, your terms are defined by what comes before it. So the way it works here for this example is they're telling you a sub 1 is equal to 5. And then the next one is a sub k plus 1 equals 2a sub k plus 1. So what's happening here is if this is the k plus 1 term, the kth term came before it because it's the kth term, the k plus 1, the k plus 2, et cetera, et cetera. So what this says is you're going to take the term that comes before it, double it, and then add 1. So you're going to double this, which is 10, add 1, that gives you 11. That's your a sub 2. Now your a sub 3 is going to be double your a sub 2 and then add 1. So we're going to take this, double it, and add 1. 11, when you double, it's 22, plus 1 is 23. And then double it plus 1. 46 plus 1 is 47. Double it plus 1. 94 plus 1 is 95. All right, so in contrast to an explicit formula, an implicit formula, you need to know other things around it in order to figure it out. So for this formula, if we wanted to know the 100th term, we'd have to know the 99th term. In order to know the 99th term, we'd have to know the 98th term. In order to know the 98th term, we'd have to know the 97th term. Oh my God, when we stop that pattern, we get it. So they have to tell you where to start. They have to give you some beginning point and then tell you how to get from one term to the next. Good with that? All right. Next one here. So we got an a sub 0. So here we're starting with an a sub 0 instead of an a sub 1 is 1. Then the term that follows that is also 1. And then they're giving us this formula. A sub k equals a sub k minus 2 plus a sub k minus 1. So if this is a sub k, that's 2 terms that came before it. That's 1 term that came before it. So here we're at a sub 2. We need to have the a sub 0 plus the a sub 1 to get this term. If that's k, that's 2 terms before that. That's 1 term before that. So we have to add a sub 0 plus a sub 1. Then a sub 3 is going to be 2 terms before that plus 1 term before that. So a sub 1 plus a sub 2 is 3. So in other words, the rule is we're adding up the 2 terms that came before it to get the term we want. So this one is 2 plus 3. This one is 3 plus 5, et cetera, et cetera, et cetera. What pattern is that? This Fibonacci sequence. All right. Any questions on that type? All right. In this chapter, we are going to be using something known as a factorial, which I'm not sure if this is something you guys have seen before or not. The notation for a factorial is the n and then the exclamation point. Okay, it does not mean n with great emotion. Again, okay, a factorial is defined by a numerical example like 5 factorial is 5 times 4 times 3 times 2 times 1. It's whatever that number is, times 1 less, times 1 less, times 1 less, et cetera, et cetera, et cetera, until you get all the way down to 1. Okay, the most immediate application that you guys might be familiar with is if you're doing counting problems, and it's like how many ways can 5 things be arranged on a shelf? There's 5 ways to pick which one comes first, and 4 ways to pick which one comes next. So one of the applications we're going to be doing later in a chapter with this guy here has to do with counting and probability. And then it also has to do with making some connections of sequences and series in ways that I'm almost positive you haven't seen before, but just take my word for it, it pops up more than just here. So in terms of what we're doing for today, right, the first 5 terms of the sequence defined by the explicit formula, and it gives us this formula. So it doesn't state that we're starting with 0, so it means we begin with 1. So n is equal to 1, 2, 3, 4, 5. So this is 1 factorial plus 3, 2 factorial plus 3, 3 factorial plus 3, 4 factorial plus 3, 5 factorial plus 3. So 1 factorial is just 1. 1 plus 3 is 4. 2 factorial means 2 times 1. That's 2. Plus 3. That's 5. 3 factorial is 3 times 2 times 1. 3 times 2 is 6. 6 times 1 is 6. And then that plus 3 is 9. 4 times 3 times 2 times 1. So it's 12, 24, 27. And then the 5 factorial I already wrote up there. 5 times 4 is 20, times 3 is 60, times 2 is 120, and then plus that 3 will make it 123. So that's our sequence. Good with that? All right, let me go back to the overview of how I started off talking about today. 9-1 is an introduction to sequences and series. Okay, 9-2, 9-3, and 9-4 are going to focus on specific types of sequences and series. Okay, 9-1 gives you the overall, what some of the vocabulary, some of the rules we're playing by. Okay, one thing is, our formulas can be explicit or they can be implicit or recursive. Explicit formulas, you can find any term you want just by knowing the number of the term. Implicit, you have to know terms around it in order to get to one you want. In some little corners of the math world, it's better to know this. Some corners of the math world, it's better to know this. One of the things we'll be concentrating on as we move through the first half of this chapter is if you know one of those, can you get one of these? If you know one of these, can you get one of those? Okay, regardless which of these two formulas you're using, unless you're told otherwise, assume N or K, depending on what the variable is, starts with 1. It's very common for it to start with 0. It's going to happen a lot, but they're going to have to tell you specifically somewhere in the problem where the instructions to start with 0 instead of 1. Okay, in this corner of the math world, a notation that maybe is new to you guys is the factorial. We talked about what a factorial means in the context of this 9-1. That would be a simple example in terms of where it would pop up. We good? All right, now specifically onto a special type of sequence known as an arithmetic sequence. So the definition that your book uses, a sequence is arithmetic if the differences between consecutive terms are the same. So a sub 1, a sub 2, a sub 3, a sub 4, just a generic way of identifying a sequence. If you take the second term and minus the first term, or the third term and minus the second term, or the fourth term minus the third term, no matter what two successive terms you pick, if the difference between them is the same, then it's going to be an arithmetic sequence. That common difference is pretty universally identified as the D. All right, so some simple examples here. Determine whether or not the following sequences are arithmetic. Well, 7 minus 3, is that the same as 11 minus 7? Is that the same as 15 minus 11? Is that the same as 19 minus 15? Yes, it is. Now, the doing the 7 minus the 3, the 11 minus the 7, that's mentally math, like a little bit awkward. Sometimes it's easier, although definition goes that way. Sometimes it's easier to think about it going left to right. 3 to 7 is plus 4. 7 to 11 is plus 4, plus 4, plus 4. It gives you the same 19 minus 15 is 4, but it's a little bit more convenient to think that left to right way. So yes, this is an arithmetic sequence, and the common difference would be 4. All right, this one here, that would be plus 3, plus 5. We don't even have to go any further. If the only thing we're answering is this thing arithmetic or not, no, it's not. Okay, 1, 4, 9, 16, 25. What are those? They're the whats? They're perfect squares. So it turns out that if it's a perfect square, that means we can model this with n squared. If it's an n to the second or any version of an n to the second, then it becomes a quadratic sequence, and that's the focus of section 9.4. So we're going to get to these guys in terms of specific formulas later this week. All right, this one here, to get from 11 over 4 to 8 over 4, that would be minus 3/4. 8 over 4 to 5 over 4, that's minus 3/4. 1/2 is the same as 2/4. So that's minus 3/4. Minus 1/4, minus 3/4 again. So yes, that is arithmetic. And our common difference is negative 3/4. So yes, yes. 4, no. All right, how about 139, 27, 81? Is that going to be arithmetic? No. How are we getting from one term to the next? What operation are we using? Multiplying. So that's going to be geometric, which is going to be the focus of section 9.3. I think, yes, 9.3. All right, next skill. If we identify a sequence as being arithmetic, can we write a formula for it? Now, your book uses this formula right here, which I'm not a fan of. If you've done this before, I think your Algebra 2 book uses that. What I'm going to show you is significantly more mental math friendly than that. Okay, if you identify a sequence as being arithmetic, you can think about it as being linear. You can model it with a y equals mx plus b, except instead of a y equals mx plus b using the variables your book uses, we're going to use this right here. All right, so here's how we're going to use this formula, and we'll go back to this as an example of how to write it. Okay, we've identified it's linear. That d is in your slope spot. So you think about that common difference is the slope of the sequence. So going back up to here, this is a sub n is equal to 4n. Now back in your y equals mx plus b days, that represents the y-intercept. Okay, the y-intercept is when x is 0. If we had the 0th term in front, what would it need to be in order to keep that pattern true? Test it. We know, for example, the 4th term has to be a 15. Plug in 4. 4 times 4 is 16 minus 1, 15. Done. So that C term is whatever the first term was. Back it up one more in order to get what would be the y-intercept in a linear world. So using that same concept to this right here, this is a sub n is equal to negative 3/4 n. If there was one more term in front, what would that have to be in order to keep the sequence true? We'd have to add 3/4, 14/4, or 7/2. There's your formula. Excuse me. Good with that? All right. Write the first 5 terms of the arithmetic sequence. Write a formula for the nth term of the sequence as a function of n. That's another way of saying write the explicit formula. Identify the 20th term of the sequence. So we've got a lot going on in terms of how many things we have to answer. So a sub 1 is negative 14. A sub k plus 1 is equal to a sub k plus 3. That means wherever you are, take the term before it and add 3. There we are. Take the term, well, here we are. Take the term before it, add 3. Add 3. Add 3. Add 3. Is that 5? Part 1 done. Part 2, write a formula for that. A sub n, that common difference is like the slope of the sequence. We add 3 each time. This term right here, or this thing that follows it, if there was one more term up in front, what would it have to be? There's your formula. The 20th term, that's the last thing they're asking us for. 3 times 20, that's 60. 60 minus 17, 43. And that's everything. Good. All right, number 2 here. A sub 1 is -5. A sub 9 is -17. So I'm going to kind of flesh this out to give you a visual. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. The first term is a -5. The ninth term is a -17. Not the first. Oh, third. I apologize. -5 is here. Since I messed that simple thing up, let's double check. A sub 1, A sub 2, A sub 3, 4, 5, 6, 7, 8, A sub 9. We're good. All right. So we know it's arithmetic. We know it has a common difference. So starting here, we have to add 1D, 2Ds, 3Ds, 4Ds, 5Ds, 6Ds. So -5 plus 6Ds gets us to -17. Make sense? So 6D is equal to, add 5 will be -12. D is -2. So this tells us our sequence goes down by 2 to get from one term to the next. So that's -7, -9, -11, -13, -15. Going in the other direction, -3, -1. Good. All right, so now we can write a formula. A sub n, -2n. If there was one more term in front, what would that have to be? +1. If you're not confident that you wrote this correctly, do a check term. So for example, we know the fifth term has to be a -9. If we plug 5 in here, we better get -9 back again. If we don't, we know we made a mistake with that. Okay, this double checks, it works. So A sub 20 would be -2 times 20 is -40. -40 plus 1, -39. So 20 for a subscript. So as far as going back to the original instructions, write the first 5 terms. So that's this. Write the formula. That's this. 20th term. That guy right there. Good. All right, last wraparound in terms of back to the beginning. Sequences is just a number pattern. Once you start adding them up, it becomes a series. So an example of getting this thing to be a series is the last thing for today. The sum of a finite arithmetic sequence, so once you're summing it, now the sequence is a series, is blah, blah, blah. So the S here stands for the sum of however many terms you want to add together. So for the first example here, we want to add together 25. So S sub 25 means the sum of the first 25 numbers. Okay, that N is the same N that's here. Okay, A sub 1 is the first term in the sequence or series that you're adding up. So for this example, it's an 11. And then the piece of information that we're going to need in order to finish up this formula is A sub n, or the 25th term, is what we need to put here. So 11, 19, 27, 35, blah, 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 blah. What you could do is extend that pattern all the way out until you have 25 terms. Then in your calculator, add up all 25 terms. Now, if that was like 7, it's not a bad strategy. You could do that on your calculator, mental math, in about 14, maybe 15 at top seconds. But 25th, that becomes quite a project. So we'll write a formula to find out the 25th term. That goes right there, do order of operations, and we're done. So 11, 19, 27, 35. The common difference is it's going up by 8. So A sub n is equal to 8n. If there was one more term in front, what would it need to be in order to keep that pattern true? A plus 3. So 8n plus 3 is the expression that defines that sequence. In order to answer this question over here, we need the 25th term. So 8 times 25, is that 200? Then 200 plus 3, 203. Get 11 plus 203 times 25 divided by 2. So 2675. That's the sum of the first 25 terms. All right, out of curiosity, did you guys do any of this in Algebra 2 last year? Now, was this stuff you did like during the regular school year, or was this like at-home stuff? You guys did this at home? Does this seem pretty familiar in terms of the same basic way you did it in Algebra 2? All right, good. All right, those of you guys at home, if you have any problems or questions, stay on and ask. Other than that, you can leave Google Meet. Tomorrow, you don't have to join in. Classwork for tomorrow is just finish up tonight's homework.